Okay, so welcome to the last talk of the day. We have Tammi Chowdhury from Canada, and she's going to talk about non-thermal leptogenesis from cosmological gravitational particle production.
Yeah, thank you very much. So today I'll be discussing some of the work we've done on the topic of non-thermal leptogenesis based off of a paper we recently put out with my collaborators Leah Jenks, Edward Cope, and Evan McDonough. So the outline of the talk will be as follows. I will begin with first motivating non-thermal leptogenesis in general, and then I will describe the type 1 seesaw mechanism. This is the framework in which we are working within. And then a key component of our non-thermal model is gravitational particle production. So I'll go through briefly the mechanisms of that. And within our paper, we derive an expression for the baryon yield y sub b, and we find that we need a phase of kination. So I'll describe this as well. And finally, I'll be able to show us a parameter space plot for viable leptogenesis. So to begin with the motivation, we know that the universe consists of baryons and we virtually have no antibaryons. And so we call this asymmetry between particles and antiparticles the baryon asymmetry problem of the universe. And this is quantified by this parameter eta sub b, where it's the ratio of the baryon number density over sometimes the entropy density S or the photon number density. And this gives a value of about 10 to the minus 10. So this captures kind of this asymmetry between particles and antiparticles. And this is an outstanding problem in cosmology. But in addition to this problem, we also have another particle physics issue that we haven't resolved yet. So we know that in the standard model, neutrinos do not have a mass. We don't have a mechanism that provides that. However, from neutrino oscillation experiments, we know that a mass is necessary for these neutrinos to be oscillating. So we need to go beyond the standard model to explain this. So a very popular framework to combine these two scenarios is leptogenesis, which I will go a little bit more in detail in the following slide. But a interesting coincidence in scales that I'll mention that will be relevant for this talk is the fact that inflation, which is probably the most accepted theory of the early universe, for many well-motivated inflation models, the energy scales are about 10 to the 13 GeV. And this is also a scale that is projected to be tested in future CMB experiments. Keeping this in mind, the leptogenesis scale for a new particle that's necessary for seesaw mechanism is also of order 10 to the 13 GeV. So this coincidence between the mass of the new particle and the inflation scale provides us also a motivation to think about a model in which these two aspects are connected. And this is going to be this cosmological particle production of these new neutrinos, these right-handed neutrinos that are necessary for type 1 seesaw mechanism. So to be a little bit more concrete, the type 1 seesaw mechanism introduces three heavy right-handed neutrinos, denoted by n sub j, where j runs over 1, 2, 3. And we can see the Lagrangian, where Y here is a 3x3 complex matrix of the Yukawa couplings. L is our left-handed lepton doublet. N is this new heavy neutrino. And phi is the standard model Higgs field. And so you can diagonalize this matrix. You can calculate the eigenvalues, the mass eigenvalues of the system, and you find that the scale of the standard model neutrino mass from this goes like y squared, which is, again, that Yukawa coupling. V is the Higgs Vev, v squared, divided by the mass of this new heavy right-handed neutrino. And so what you can immediately see is that as you increase the mass of the right-handed neutrino, you get a smaller standard model neutrino mass. And so from experiments, we also know that the standard model neutrino mass, so the left-handed neutrinos, are small, so they're order of 0.1 eV. And so to accommodate for this observed value in our universe, the right-handed neutrino mass should be about 10 to the 13 GeV. So this is how the seesaw picture kind of comes in. One goes up, the other goes down, essentially. So now a very brief description of inflation, just to set the ground here. Inflation is the very fast, the exponential expansion of space-time in the first moments, 10 to the 30 seconds of the universe. And it became a very popular model because there were outstanding problems in cosmology, such as the flatness problem and the horizon problem. So just briefly, the horizon problem entails the fact that if you have two patches in space, they, in theory, should not be causally connected. They're too far apart. However, we have seen there's temperature correlations between the two patches, and this was a mystery. This should not have been the case. However, if you introduce inflation, this resolves it because if you go back early in time, these two patches were in fact causally connected, and therefore we see that now. So inflation has quickly risen to kind of the accepted early universe idea. And so the inflation scale we denote that by the end of inflation h sub e, and we have the scalar to tensor ratio R. And so essentially delta T is the primordial power spectrum of gravitational waves, and delta sub S is the curvature from scalar metric perturbations. And so the CMB temperature anisotropies provide a value for the scalar perturbations of order 10 to the minus 9. And then the tensor perturbations is set by this inflation scale h sub e. And if we take that to be about 10 to the 13 GeV, as I mentioned, you can calculate this ratio, R, which is close to 10 to the negative 3. And this is projected to be at a precision level of future CMB experiments. So this is interesting for us because this allows us to validate or disqualify our model. And that's always a good thing for falsifiability. And so as I mentioned, for the non-thermal leptogenesis, we need to produce these new right-handed neutrinos in some way that's not from the thermal plasma. And so this is when gravitational particle production comes in hand. So a natural outcome of expanding space-time is the production of particles purely through gravitational interactions. And so this is a neat feature of curved space-time. If you have one vacuum state that in one observer would state that it's a vacuum state, in a different observer's frame, it would be occupied at some late times. So these two observers would not agree with what is in fact the real vacuum state. And to connect these two, we use these Bogoliubov coefficients, alpha and beta. And due to the expanding space-time, you get a mixing of the positive and negative frequencies. And this produces the production of particles just through the curved space-time, the geometry of that. And so here in the purple box, we have psi, if we have some spin 1/2 field. So this is our heavy right-handed neutrino. You decompose it into its mode functions, U and V. This is kind of the representation of this spin 1/2 field. And that Bogoliubov coefficient, beta sub k, if you can calculate the co-moving number density of these neutrinos, these heavy neutrinos, as essentially the squared value of that beta coefficient, that Bogoliubov coefficient, imposing some initial conditions. We call them the Bunch-Davies initial conditions. But this is the expression for the number density that will be produced from this gravitational mechanism. Now, going back to leptogenesis, there are three conditions, these three Sakharov conditions that must be satisfied. The first being baryon or lepton number violation. So in this case, we have these heavy N, these are the right-handed neutrinos that decay into standard model leptons, as well as the Higgs, denoted by phi here. So the N, the heavy neutrinos, are Majorana, so they don't carry a lepton number. And so as a result, since they decay into leptons, we are violating lepton number here, therefore satisfying the first Sakharov condition. The second condition is CP violation. So you need to have some difference in the rate in which the right-handed neutrino decays into a lepton versus an anti-lepton. And this is quantified through the parameter epsilon j here. So this is our CP violating parameter. And the third condition is out of equilibrium conditions. And so this is satisfied because we're working in the non-thermal limit. So our reheating temperature of the universe is significantly smaller than the mass of our right-handed neutrinos that are decaying away. Now, something to be vigilant about is also the Davidson-Ibarra bound. And so this is essentially telling us what is a limit on how much CP violation we can have in the system. This is constrained by the neutrino mass, or the atmospheric mass splitting of the neutrinos within the standard model. And this is taken to be about 0.05 eV. And this is also a function of the mass of the new right-handed neutrinos. So given that we take the mass scale of N to be 10 to the 13 GeV, you find that the maximum epsilon, which is our CP violation, is about order 10 to the -3. So really what this is a statement is you can't arbitrarily have a large amount of CP violation. This will be constrained by m nu as well as the mass of the new particle that we're introducing. And as I had mentioned, we derive in the paper the baryon yield, so YB. This is the number density divided by the entropy. And if you start with the evolution, so here we have an expression for the Hubble rate at reheating time. So the subscript RH is for reheating, and HE subscript E is for the end of inflation. It evolves with this omega, which is the equation of state of the universe. And we also assume that there is no entropy injection after reheating time. And so the entropy should be a conserved quantity. And so we have that second equation in the first purple box. Using these two relationships, you can then find this Y of B expression. And the takeaway here is that the yield is exponentially grows with this omega, this equation of state. And so the closer we are to 1, the larger yield we get for the baryon asymmetry. And so the case where W is equal to 1 or omega is equal to 1 equals is essentially a kination phase. So kination is when all of the potential energy of the inflaton, the field that's driving inflation, is now converts it into kinetic energy. And so we don't necessarily have to have kination, like W is equal to 1, but for our work, we suppose this and take W is equal to 1 for our work. And this prefactor of 28/79 is accounting for the conversion between the lepton asymmetry that's being generated from the decays of the right-handed neutrinos that will then be converted into the baryon asymmetry through the non-perturbative effects of this Faloin process. And yes, so this A cubed n sub n here is the number density, the co-moving number density that's produced from the gravitational production. So here, to give a more concrete picture of that production, on the y-axis, we have that co-moving number density. And on the x-axis, we have the mass of the right-handed neutrinos with respect to the Hubble scale at the end of inflation. And what you see is that when the mass is close to the inflation scale, we kind of get the maximum amount of production, and that's about 10 to the minus 3. In the dotted lines, we have kind of a analytic expression to map onto how they grow and fall. So now an important thing for tracking the number densities or the evolution of our right-handed neutrinos, as well as the subsequent lepton asymmetry denoted by this capital L, is using the Boltzmann equation. So in the first equation, we have the tracking of the right-handed neutrinos, and gamma is the decay rate of this, and sigma v sub 1 and 2 are the cross sections of scattering interactions. And these scattering interactions can cause washout because it could recreate the right-handed neutrinos. So that should be closely accounted for. And so that's all contained in the first Boltzmann equation. However, these cross sections actually turn out to be quite negligible for our work in particular, mainly due to the fact that our reheating temperature is so much smaller than the mass of our right-handed neutrino. And so it doesn't thermalize and wash that out in the way that thermal leptogenesis usually has to be very vigilant of these washout processes. So really these first two equations reduce down to the smaller, much easier two differential equations at the bottom there. And so to describe the evolution of these fields, so in green we're showing the cosmological particle production of the right-handed neutrinos. So there's a stark increase, they oscillate, and then they stabilize to some value. This is then shown in blue. The decays of these right-handed neutrinos, they decay once inflation ends, and we're in the phase of kination now. And as the blue curve is decaying, these neutrinos are decaying, this is producing the lepton asymmetry, which subsequently produces the baryon asymmetry shown in the purple curve. And in the blue dashed curve, we see the the equilibrium number density of these right-handed neutrinos. And as expected, this curve is always significantly lower than that of the number density produced gravitationally or like non-thermally. So it also reinforces the fact that that washout effect shouldn't be so relevant for us. And at reheating, we have an entropy jump, and so the yield y of b, you see a steep decline just because y of b is defined to be over the entropy density. And so once the reheating stabilizes, we finally get our value for the observed baryon asymmetry. And this, given our parameters that's used for this plot in particular, shown at the top of this figure, we are able to obtain or match the results of observed baryon asymmetry yield. And finally, in this plot here, we show the parameter space for leptogenesis. In the white shaded region, this is the allowed region. In red, we show the excluded parts because of the limits on kination. So there's been other authors who have shown that there is a limit on how long the duration of kination can last. And they find that it has to be less than 10 E-folds. And so from that, we exclude that anything below that value, so in red. In green, this is also an exclusion from CMB data. This is showing us the R value, that ratio of tensor to scalar ratio. So that's also excluded. And in the red dashed lines, we show the Davidson-Ibarra lines. So this is showing us where leptogenesis is viable given the value we take on with respect to epsilon of Davidson-Ibarra bounds. So above that, we just don't generate enough baryon asymmetry to accommodate for what we observe in the universe. And then in blue, this is thermal production. So this is not in the realm of what we are investigating. And yeah, so in summary, hopefully I've been able to show us that through the non-thermal production of the right-handed neutrinos, we can have them decay into the lepton asymmetry, and that's generating the baryon asymmetry, and it accommodates for what we observe. And this will be testable in future CMB experiments, hopefully at the scales in which we are looking at least 10 to the 13 GeV for inflation scales.